this point in the course, we're ready to zoom out from the scale of parsecs, the typical distance between stars in our galaxy, to the scale of kiloparsecs, where we can take in the view of the entire galaxy. Seeing the Milky Way on a dark, clear, moonless night is always a treat. You can see why our ancestors thought it looked like spilled milk. It's the combined light of billions of stars too distant to resolve with our eyes. And the dark patches are interstellar clouds of gas and dust in the foreground. From a given point on the Earth, we only see a section of the Milky Way, but we can piece together an all-sky view. In doing so, we have the usual map-making problem of displaying a spherical surface, the celestial sphere, on a flat page. Astronomers like to use an equal area projection called the Hammer-Eatough projection, which is sometimes used to display the Earth's surface. An all-sky map of the Milky Way shows a flattened distribution of stars, like a pancake or a disk. When we look along the galactic equator, we're looking within the plane of that disk at multitudes of distant stars. When we look above or below the disk, we hardly see any stars by comparison. We also see a brightening in the middle of the map. That's the center of the galaxy, where the disk thickens into a bulge, a sort of elliptical blob of stars. An all-sky map based on infrared images rather than visible light gives a clearer view of the bulge in the disk because infrared radiation has an easier time penetrating through the dust clouds. A schematic diagram of the Milky Way helps us understand the different parts. At the center is the black hole, Sagittarius A star, with a mass of 4 million suns. It's surrounded by the stellar bulge, a few kiloparsecs wide, and a mass of 20 billion suns. Then there's the disk, with a total mass of around 70 billion suns. The sun is in the disk, about 8 kiloparsecs from the center. Outside the plane of the disk, there aren't as many stars, but there are some. And interestingly, they're arranged in a more spherical distribution, called the stellar halo. That's also where you find the globular clusters, each with up to 1 million stars packed into a tight ball. I wish I could show you a picture of the Milky Way from afar, but of course we have no way to obtain such a picture. It's like trying to take a picture of your house when you're trapped inside. You can't. But what you can do is to look out the window at neighboring houses, which are probably like yours. And we can do the same with galaxies. Andromeda is the nearest big galaxy. It's only 2.5 million light years away, or 0.8 megaparsecs. The Milky Way probably looks something like Andromeda. Looking further away, we can find galaxies that we're viewing from higher above the disk, giving us a better view of the spiral patterns of stars and gas and dust. Very often, the spiral arms appear bluer than the bulge. That's because the disk is where new stars are formed, including blue massive stars. The bulge is mainly older stars, so all the blue and massive stars are gone. They already evolved into red giants. The spiral arms are also dotted with colorful nebulae, marking the locations of star-forming regions. A spectrum of a disk galaxy reveals that the disk is rotating. You can tell from the Doppler effect. Half the galaxy is approaching us, so it's blue-shifted, while the other half is receding and red-shifted. The Sun makes a complete orbit of the Milky Way every 200 million years, traveling at an average speed of about 220 kilometers per second. In addition to disk galaxies, we find a lot of galaxies that look like featureless blobs of stars, all bulge and no disk. They're called elliptical galaxies. The stars in elliptical galaxies tend to be older and redder than in spirals, and they don't all rotate together or show much coordinated motion at all. Instead, the stars are orbiting more randomly in all directions. Those are clues that elliptical galaxies are older than disk galaxies. They've had more time for their stars to age and for their orbits to randomize. Current thinking is, when two disk galaxies collide, the resulting train wreck becomes an elliptical galaxy. We'll return to that point later in the lecture. First, I'd like to show you some different kinds of galaxies, variations on the themes of spirals and ellipticals. There are elliptical galaxies that are cut through with dark dust lanes, which are usually more characteristic of spirals. There are disk galaxies that don't have any spiral arms. There are disk galaxies in which the spirals attach to the bulge through an elongated bar of stars. And there are some spirals that don't seem to have any bulges at all. Galaxies have more diverse forms than stars. They're like the orchids of the universe. Both their formation and their evolution are more contingent on circumstances than for stars. So we shouldn't expect to be able to understand them with simple equations. But we can make some progress. The first step is to think of a galaxy as a fluid or a gas. But instead of being made of atoms or molecules, it's made of stars. Now, that's a mind-bending idea. A star is millions of times more massive than the entire Earth, but galaxies are trillions of times larger still. So yes, when we zoom out to galactic scales, we can treat the stars as microscopic particles of a fluid. In a way, we're reverting to the original description of the Milky Way as a stream of milk. The fluid-like nature of galaxies is especially clear in images where two galaxies are interacting with each other. In some cases, the tidal gravity from one galaxy causes stars to spray out of the other galaxy, forming long, thin streams like a fountain. In other cases, the collision of two galaxies launches spherical waves into the pattern of stars, which look like wispy bubbles and curtains. But there are major differences between an ordinary fluid and a fluid of stars. One of them relates to the mean free path, the average distance a particle can travel before colliding with another one. The mean free path of a nitrogen or oxygen molecule in the air is about 1/10 of a micron. In the sun, the mean free path of a photon is about 1 millimeter. In both cases, the mean free path is much smaller than the scales that we're usually interested in. That's why we can assume that the particles rapidly exchange energy and achieve thermal equilibrium, and that each position can be associated with a well-defined temperature. How about galaxies? How far does a star travel on average before it hits another star? Well, the defining criterion for the mean free path is n sigma L equals 1, where L is the mean free path, n is the number density of particles, and sigma is the cross-section, the area of the target that a particle has to hit for an interaction to occur. In the neighborhood of the Milky Way, the density of stars is about 1 star per cubic parsec. So what about the cross-section, sigma? Imagine throwing a star at another star of the same radius r. For a collision, the centers of the stars must come to within a distance 2r of each other. So the target area is a circle of radius 2r, and the collision cross-section is pi times 4r squared. Using the radius of the Sun, the mean free path comes out to be 2 times 10 to the 14 parsecs, whereas the size of the Milky Way is only 2 times 10 to the 4 parsecs. According to this calculation, the Sun could cross the Milky Way 10 billion times before it hit another star. Now, this calculation is a little unfair. Stars don't have to physically touch in order to deflect each other. They pull on each other with a long-range force, gravity, unlike the idealized billiard ball particles of an ideal gas. So the true cross-section for stellar interactions is larger than 4 pi r squared. But even when you take that into account with a more complex calculation, the fact remains that a typical star in the Milky Way is unlikely to ever hit another star. Stellar collisions only occur in unusually dense groupings, like globular clusters, or when they're caused by effects other than long-range gravitational forces, such as the energy loss due to tidal forces or gravitational radiation. The bottom line is, we can think of a galaxy as a gas of stars, but it's not an ideal gas. It's a collisionless gas. A star's trajectory is determined not by close encounters with other stars, which are vanishingly rare, but rather by the combined gravitational field of the entire galaxy. The spatial distribution of all the stars determines the galaxy's gravitational field, which then determines the motions of the stars and changes their spatial distribution. Everything gets tangled up on large scales rather than small scales. That's what allows for more complicated behavior than a gas, including all of the wonderful patterns and instabilities that we see, like spiral arms, bulges, and bars. Another big difference between an ideal gas and a collisionless gas relates to temperature. The temperature of an ideal gas is defined to be proportional to the average kinetic energy associated with the random motions of the gas particles. The average value of 1/2 mv squared is 3/2 kT, where K is Boltzmann's constant. We could try to do something similar for stars in a galaxy. We can define the dynamical temperature to be proportional to the average of 1/2 m sigma v squared, where m is the mass of a star and sigma v is the velocity dispersion, the spread in velocities of the stars at a given location. We can measure the velocity dispersion by obtaining a spectrum of all the starlight from a given location in the galaxy, and then looking at the width of the absorption lines, their spread in wavelength. This blurring of the absorption lines is produced by all the different Doppler shifts of individual stars at that location. The concept of dynamical temperature gives us a different way to think about galaxies. The stars in both elliptical and disk galaxies have speeds of hundreds of kilometers per second. The difference is that ellipticals are dynamically hot. The stars fly around randomly with a large dispersion. Disks are dynamically cold. The stars rotate all together with less variation in velocity between neighboring stars. A spiral galaxy, then, is analogous to a cold, swirling glass of milk, while an elliptical is more like a hot puff of smoke. But this analogy with ordinary temperature breaks down if you push it too far. For example, in a highly elongated elliptical galaxy, the velocity dispersion is higher when you measure the components of velocity along the long axis as opposed to the short axis. So the dynamical temperature at a given location depends on direction. That's pretty weird. And with galaxies, there's no exact equivalent of thermal equilibrium. If you stir up an ordinary gas, it eventually returns to a steady state of constant temperature, with the velocities of the gas particles approaching the Maxwell-Boltzmann distribution, as we discussed in Lecture 8. But in a galaxy, there is no steady state. In the fullness of time, a system of gravitationally interacting particles that can exchange energy with its surroundings will tend to eject some particles and have the rest collapse toward the center. It's a mathematical phenomenon called the gravothermal catastrophe. All of this is what makes galactic dynamics such a fascinating and complex subject. Instead of diving deeper, though, we're going to derive an equation, the virial theorem, that will serve as a life preserver, something that we can cling to avoid drowning in the details. Do you remember when I said earlier that stars have a negative heat capacity? That when they lose energy, they heat up? The virial theorem is the mathematical expression of that concept. Imagine a bunch of particles flying around with different speeds and trajectories, but held together by their mutual gravity, so they can't escape. The virial theorem says that if you watch this system for a long time, then on average, regardless of the details, the total kinetic energy will be equal to -1/2 of the total potential energy. It applies to any isolated, gravitationally bound collection of particles, whether it's the atoms in a star, the stars in a galaxy, or a cluster of thousands of galaxies. That means the time invested in understanding the virial theorem leads to a big payoff. To prove the theorem, we start by defining the virial as the dot product of momentum and position summed over all the particles from 1 to n. The name virial comes from a Latin word for something like strength, although momentum times position doesn't have any obvious physical significance. We'll see why it's useful by taking the time derivative. Using the product rule, we get m dv dt dot r plus mv dot dr dt. In that first term, m dv dt is mass times acceleration. That's force. So we can replace it by f dot r. And in the second term, dr dt is velocity, so we can rewrite that term as m times velocity squared. And now our destination is starting to come into view. The sum over mv squared is twice the kinetic energy. Less obviously, the sum over f dot r will turn out to be the total gravitational potential energy. To show that's true, first let's consider the simplest case of just two particles, n equals 2. We'll use a coordinate system in which particle number 1 is at the origin. That way r1 is 0 and we can ignore the first term in the sum. For particle 2, instead of r2, we'll just write r. So the sum over f dot r is simply f2 dot r. F2 is the force of gravity on particle 2, which we can write as minus g m1 m2 over r squared times r hat, just like we did back in lecture 5. R hat is the unit vector pointing in the direction of increasing r, and the minus sign is there because the force of gravity is attractive, pointing back toward the origin. Since r hat, dotted with the r vector, is simply r, we end up getting minus g m1 m2 over r, which we recognize as the gravitational potential energy associated with the interaction between the two particles. When we have n particles instead of just 2, the force on the ith particle is the sum of the forces from all the other particles, and the sum over f dot r becomes the total gravitational potential energy associated with the interactions between every pair of particles. So we've made progress. The rate of change of the virial equals the potential energy plus twice the kinetic energy. Now let's take the long-term time average of both sides of the equation. Here's where we'll use the fact that the system is bounded. The particles can't escape. That means the virial itself must be bounded. It's a number that's restricted to a certain segment of the number line. And if that's true, then the rate of change of the virial must eventually average to 0. After all, the average rate of change of the virial is equal to the final value minus the initial value divided by the time. If those two values are always finite, then by making the time arbitrarily long, we can make the average arbitrarily close to 0. Therefore, the long-term average of gravitational energy plus twice the kinetic energy equals 0, which leads to the virial theorem as advertised. Another way to express it is in terms of the total energy. In general, the total energy is the sum of kinetic and potential. In this case, it must be a negative number because the system is bound. And since we now know the potential energy is -2 times the kinetic energy, the total energy must be equal to minus the kinetic energy. The minus sign means that if we have a system of gravitationally bound particles, and we inject some energy, raising the total energy closer to zero, then after the system readjusts, we'll find the kinetic energy has gone down. That's weird, because when we inject energy into an ordinary gas, the particles speed up. But here, when we eject energy, the particles slow down. That's what we mean when we say gravitationally bound systems have a negative heat capacity. One example is a spacecraft orbiting the Sun. If it briefly fires its rocket engine, increasing the total energy of the orbit, the result is to lift the spacecraft into an orbit with a larger semi-major axis, where it moves more slowly on average. Another example is the core of a star, where the negative heat capacity is a stabilizing mechanism. If there's a temperature fluctuation that makes the core hotter, the fusion reactions speed up, injecting extra energy into the system. The core responds by expanding and cooling down, reducing the nuclear reaction rates back to normal. That's why fusion at the cores of stars is so steady and long-lasting. Remember, the interior of the Sun is more like a collection of toasters than a nuclear war. The flip side is that if the star loses energy by radiating more than it's producing, the core shrinks and heats up. And that was a crucial part of our discussion of stellar evolution back in Lecture 16. Now, how is all of this relevant to galaxies? Let's say we're studying an elliptical galaxy. We'd love to know the orbits of all the stars and how they change with time, but that's a job for a trained galactic dynamicist. But thanks to the virial theorem, we know that regardless of the details, the kinetic energy is -1/2 of the potential energy on average. From that, we can write a useful order of magnitude expression. For the kinetic energy, we'll write 1/2 m sigma v squared, where m is the total mass of the galaxy and sigma v is the velocity dispersion. For the potential energy, we'll write gm squared over r. In general, there should be some numerical factor like 3/5 or pi over 8, or something that depends on how the stars are arranged. But our expression captures the right order of magnitude. Then we can solve for m, giving sigma v squared times r over g. This is useful because we can measure r based on the galaxy's angular size and its distance. And we can measure sigma v by looking at the widths of the absorption lines in the spectrum. Then this equation allows us to estimate m, the mass of the galaxy, which we otherwise wouldn't be able to measure. The lesson is that for any gravitationally bound system, if we measure the overall size of the system and the spread in velocities, we can estimate the total mass. Now, to do that, we do have to assume the observed state of the system is representative of the long-term average. This would be false if we were observing the initial formation of the system, or if it were about to collapse. But subject to that caveat, the virial theorem can be used to measure the masses of elliptical galaxies, the bulges of disk galaxies, star clusters, and even the black holes that reside at the centers of galaxies. In our own galaxy, we can see the individual stars going around the central black hole. But other galaxies are too far away for that. Instead, the evidence for central black holes comes from the spectrum of the combined light of the whole swarm of stars surrounding the black hole. We can measure the velocity dispersion of the stars as a function of distance from the center of the galaxy. Within a few parsecs of the center, the velocity dispersion shoots up by hundreds of kilometers per second, implying that the stars are buzzing around something massive and compact. In some galaxies, the stars or the gas surrounding the black hole show a more coherent rotation pattern, which can be measured from the overall Doppler shifts in the starlight. Within the central few parsecs, the rotation velocity also shoots up by hundreds of kilometers per second, again implying the existence of a large central mass. The black hole masses range from 1 million to 10 billion solar masses. That's why they're called supermassive black holes. But it's important to keep in mind that these black holes are featherweights compared to the mass of the entire galaxy. Sagittarius A star has a mass of 4 million suns, but the Milky Way has 100 billion stars. So we should not think of a supermassive black hole as the dominant anchoring mass of a galaxy, in the way that the sun anchors the solar system. The only stars directly affected by the gravity of the central black hole are the tiny minority within the central few parsecs. We don't know when or how those supermassive black holes formed. But one of the most important clues is a correlation that's been observed between the mass of the black hole and the much larger mass of the surrounding galaxy. More massive galaxies host more massive black holes. This is usually presented as a chart of black hole mass versus velocity dispersion. But in this case, the velocity dispersion being plotted is not for the swarm of stars in the immediate vicinity of the black hole. It's the velocity dispersion of stars over a much larger region, like the entire bulge of a spiral galaxy. On a logarithmic chart, the data points follow a line with a slope of about 5, meaning that the black hole mass varies as the velocity dispersion to the 5th power. Nobody's sure what that means. It's not obvious why the black hole, whose direct influence only reaches out a few parsecs, should be related to the motions of stars kiloparsecs away. Most likely, the formation of the black hole was connected to the formation of the surrounding galaxy. I'll have more to say about supermassive black holes in the next lecture. For the rest of this one, we'll stay with the subject of galaxy dynamics. We now know to think of a galaxy as a collisionless gas of stars. The stars hardly ever have close encounters. They interact through long-range collective forces. But what about the interactions of galaxies with each other? The Hubble Space Telescope shows us that when we look in any direction of the sky, we see galaxies galore, about one big galaxy per cubic megaparsec. So when we zoom way out to the gigaparsec scale, entire galaxies play the role of the fundamental particles of the universe. So should we think of the universe as a collisionless gas of galaxies? It turns out the answer is no. Galaxies often interact and collide. The typical spacing between galaxies is about 50 times the size of an individual galaxy. That's much more closely packed than the stars within an individual galaxy, where the spacing between stars is millions of times larger than an individual star. Calculations of the mean free path show that over 1 billion years, a typical galaxy has a few % chance of smacking into another galaxy. Which implies that if you look at hundreds of images of galaxies, you'll see some close encounters. And we do. We see pairs of galaxies in the midst of collisions that last hundreds of millions of years. The tidal force of each galaxy on the other causes their stars to spill out in curved arcs or get distorted into blobby comet-like shapes. Some of my favorites are galaxies that look like elliptical galaxies, but surrounded by a ring of stars. The ring is probably a spiral galaxy that got too close, and the tidal gravitational forces strung it out into a complete circle, sort of like a galactic scale version of the rings of Saturn. The bubbles and shells that we see around some galaxies are thought to be an after effect of galaxy mergers. The smaller galaxy oscillates inside the bigger one for a while, causing stars to be ejected in spurts. before the two galaxies merge completely. Mergers were ubiquitous early in the history of the universe when galaxies first formed. All large galaxies, including our own, formed through the mergers and accretion of smaller galaxies. Many elliptical galaxies were probably created by the mergers of two disk galaxies. Computer simulations bear this out. You can follow the progress of simulated galaxies over billions of years as two disk galaxies approach each other, collide, emit streams and shells of stars, and then gradually come together and sink in their combined gravitational well, forming an elliptical. Another way to put it is that when two dynamically cold galaxies hit each other, the collision converts all of that galactic-scale kinetic energy into the random motions of individual stars, resulting in a dynamically hot elliptical galaxy. In that sense, galaxy collisions are inelastic, not at all like billiard balls knocking into each other. It's more like two globs of cold milk crashing together, splattering and heating up. Wouldn't you love to see a galaxy collision up close? Well, it turns out the Andromeda Galaxy, the nearest big spiral galaxy, is headed straight for the Milky Way at 110 kilometers per second. Over the next 4 billion years, Andromeda will loom larger and larger in the sky until the two galaxies begin merging into a single galaxy that some have already named Milkomeda. But as we've seen, there's no reason to be concerned. Even during this galactic pileup, the probability that the Sun will have a close encounter is extremely low. Our descendants will be able to just relax and enjoy the view.